Okay, let's go. Hello everybody, my name is Alexandre, and today I will talk to you about frailties in propensity score matching and how we propose to fix them. I don't know if it's lucky or if the chairs and organizers are very good, but I will answer maybe some of the questions of the previous talk, so that's fortunate. This is work I've done mostly alone, but I was joined by Andres from Rakuten in the end, and it's published in as a paper in ECML PKDD. And because it's research work, it means I will have ugly figures. We'll talk first about my company. My company does predictive maintenance for the heart. Basically, we remote monitor the pacemakers of people and try to send them to the hospital before they need to go to the ER. And one day my boss come to me and say, okay, Alex, I need you to take past data, so take all the patients we had before, and try to evaluate if our treatment is good, so that we can tell the health authorities that we save lives and get reimbursed. That's the key point for medical companies. And even though I'm not a statistician, I'm an engineer, I can do anything, of course. I'm an engineer. So I decided to take on this challenge. So the first thing I've done is just to see how people usually do that and do the same thing as them, because we don't want to reinvent the wheel. The first thing when you want to deal with biased data, we are sure to have biased data, for example, in the medical domain, for treatment that are not reimbursed because they are usually given primarily in private practice rather than hospitals. So how do we do that? Well, we have a population of people that have different covariates, age, gender, comorbidities, and we have a distribution for our controls and for the people that have been treated, and obviously they are different. So what we do is that we use some measure to know how different they are and if we need to correct the population. Here, we usually use standardized mean difference, which is basically the difference of the means divided by the pooled standard deviation. The problem when we have the difference is that we can say, okay, they are different, but it doesn't tell us how to correct. The best thing we could have is a good summary of these differences, maybe in one score, and that's what actually was proposed in the 80s. And it's the propensity score that was presented before, which is basically the probability for each patient to be treated given his covariates. If we have a completely randomized experiment, we expect to have 50% chance for each patient to be treated because it's completely random. Obviously, if we live in a real world and with models, so we could expect having Gaussian centered on 50%. But when you have a selection bias, you will end up with propensity curves that look like that. And you can obviously see that you have a problem. So once we have measured this bias and this propensity, the question is, what can we do to correct it? You had a presentation just before about learners that can do that. There are many ways to do it. Today I will talk about one that is used a lot in studies that I had the occasion to see that was submitted to the health authorities, and it's called propensity score matching. The principle is that we have two populations, controls and treated, and in order to have populations that are exchangeable, we will make pairs of patients. So for each patient in the treated population, we'll try to find a matching one in the control population. And by doing this matching, we end up with two populations that can be compared without further problems. And obviously, this is expected to correct the distribution of propensity scores. This is great, but there are different ways to match people. And you've seen before there are different ways, different models to compute propensity. And the question is, does it have an impact on the estimated effect? Here I just put a toy data set, and we already see I propose two matching, so the numbers are propensities, and you see that the red and blue one seems reasonable. Is there one that is better than the other? It's hard to tell just with these numbers. And if the average treatment effect estimated between the two is not the same, then we may have a problem, because it means that the method can impact the result that we get. I was wondering if this was a problem, so I just went on and tried by myself these methods. So here you have one of the ugly figures. It's a summary of the pipeline, standard pipeline you can find to apply propensity. It's actually pretty standard. The first step, I don't know if I have, no, okay, you cannot see my mouse. The first step is covariate selection and engineering. So you have your covariates, you have your categories, maybe you want to encode them in some way to input them in your model. Then you select your propensity model. Once you've estimated it, you need to validate it. And if it's not valid, you want to go back either to take another model or to maybe add a new feature, remove a new feature, change the way you encoded a feature. Once you have a propensity model that is working and valid, you can move on to the matching technique. Once again, you have a lot of matching techniques. You have to pick one, validate it again, and hopefully you end up with one result. I've talked a lot about validation, and we have specific rules when we submit models to the health authorities. They have listed it clearly, what is the minimum they expect. First, for propensity methods, they want something propensity to be estimated, which is logical, but they don't tell anything about the model. Can be logistic regression, trees, whatever you want. For the propensity, you have to check for the common support, which is that basically ensure that you have a counterpart for each patient in the other population. If you look at the literature, you'll see a lot that this can be done with a visual check with no more details. So it's hard to have a quantitative criterion on this one. And checking the balancing properties. After you have operated the matching, you must compute again the difference in distribution, and you should find lower values, and hopefully values below 10% for that's the threshold set by the health authorities. And because I'm not a statistician but an engineer, and I had approximately 100 methods, 100 combination of different methods to estimate propensity and matching, I've just run them all to see what would happen. And we have this figure here. Because we are close to lunch, I decided to take a voucher data set, not horse diarrhea, for example. It's not a good taste. So here you have, it's a data set that comes from Groupon. And the reference values is, if you give no voucher, you get 9,000 approximately sales. Each point here is a method that is deemed valid, that has a valid propensity model, and that went through the matching. The red bar is the balancing property threshold. So what is above is invalid. We see that we have only 2 models with valid propensity that have invalid balance in the end. And we have a lot of them at the bottom, 10 to be exact. And the problem here is that the minimum value is plus 2,500, so plus 25%, and it can go up to plus 40%. So obviously, if I am the person who developed this campaign, I will take the plus 40%, depending on what I want to show to my stakeholders. And for me, this is not a good signal when you can choose can basically choose the effect that your treatment have, especially since we are in the medical domain and pharmaceutical labs are not known to be very benevolent. So what we decided is trying to craft a new validation metric, and in particular try to see if we can do something with the treatment. I will go back to the propensity score estimation. When you have covariates, it was said before, you can have features that will influence the treatment assignment, so that are important basically for the estimation of the propensity. And you have some that may impact the outcome. It is advised to put all of them in your propensity estimation model. And I've said it before already. For the features that will impact the treatment assignment, we check the common support and we check the feature balance in the end. So we have 2 checks. For the one impacting the outcome, we have the feature balance, obviously. We want them to be balanced in the end. But is the outcome corrected properly? It's hard to tell. And the reason has already been evoked in the previous talk. We have no ground truth for treatment. We have 2 populations, and we don't know the real treatment effect. So I tried something to put myself in a case where I know the treatment and see if I can get some information. Let's go back to the problem, controls untreated. We have different distribution, and we know that that gives us a difference in, between features, also a difference in the treatment, but this is a biased difference. What I want to do to be in a situation where I can know the treatment is that basically I will forget one of the population, here the controls, and what I want to do is to create an artificial task where that will look like the one that I'm trying to solve. So I take the controls, I split them by random. I usually try to respect the ratio of population. And there I see I have a difference in features and estimated treatment. And I will change it progressively. Here you can see that some characters are becoming red and blue. And I will do that until I find something that looks like the reference task. So I have a task, an artificial task, because there is a difference here. We see that there is a bias because my estimated treatment effect is not 0, despite the fact that I took both groups from controls. So that's the way we get the ground truth. If you take 2 groups from the same population, the difference in treatment should be 0. And if you do that, you obtain an artificial task. The problem with that is it's a stochastic process, and you may be lucky or not. So you want to repeat it a lot of time and maybe take the average in the end. So to summarize, this is a metric we call A2A to reference the A-B test, because here we are comparing the A population to itself. The fundamental idea is that if I take one population and take 2 splits of it, I should have a treatment of 0. And now what we want to know is, okay, if I have a method that is good at correcting the bias on this artificial task, so finding the 0, is it good for my original task? That's what we will check after. So the full pipeline to compute the metric is actually we automated all the pipeline you've seen because we need to compute a lot of pipeline. And we create 100 artificial tasks. We run each bias correction on each task, and in the end, we take the average. Now we have 2 metrics. We have the standardized mean difference, and we have the A2A. We'll see how we can combine them. So I hide a bit the fact that in the previous graph, actually, the x-axis was the A2A metric. And the best methods are in the lower left corner. Obviously, now we have a trade-off between the 2 metrics, and we want to select a bunch of valid models to be in the same spirit as the SMD, that is a method that can select some model that should be the most accurate. For that, we tried 2 things. The first one is run a DB scan, so a clustering method, and take the cluster where there is the method with the lowest A2A. The other one, because we have a trade-off between methods, is to take the Pareto front method. So we select all the methods that are the best in either of the metrics. That's 2 ways we have to restrict the selection of methods more than what the SMD usually does. In order to be able to say that this is a valid approach to select a model, we created synthetic data, and we vary the number of confounding variables. We go from 0, where you have some features that are impacting treatment selection, the other the outcomes, up to 10, where all the features are impacting both of them. And once again, we didn't reinvent the wheel. We actually took the synthetic data generation from the package causal ML. So let's now dig into the result. Once again, it comes from a research paper, so it's a bit dry. We have 2 columns here. We have the range of estimated treatment values. By range, I mean the difference between the red and blue method I showed before. So we take all the valid methods. We take the one that has the most optimistic outcome and the most pessimistic, and we take the difference. And this is a quantity we want to reduce. We also have the true estimation error. We can only have it for the synthetic data, because obviously we masterize every parameter in this data generation. And once again, this is something that we want to have the lowest possible. And here you have the values for the SMD that are already there. So this is a standard pipeline. What we can see first is that when we apply additional selection, so with either of our strategies, either SMD, A2A, or Pareto, we reduce the range. And that's logical because basically we will select less technique than the other method does, so it's an obvious result. The thing is that in this restricted set of methods, we are more likely to obtain the best model because the average error is lower. And one thing we start to observe is that the number of confounders has an impact on the strategy that is the best one. So SMD A2A seems to be better for a low number of confounders and Pareto for the high number of confounders. In order to dig up into this result, we looked at what happens if we take the one model only, the one with minimum A2A and minimum SMD. And here we see that usually when we take the minimum SMD, we obtain models that are better when there are a high number of confounders. And when we take A2A, we obtain the one that works better when there is a low number of confounders. And that may explain what we see before, because the Pareto method has a tendency to select more models with low SMD, because it goes with a long tail. And the SMD A2A is more balanced. Finally, if we look at the results on the real data sets, we see on the Groupon data set, we go from more than 1,000 euros in difference to 600. Still not great, but it's lower, 2 times lower. And for other data sets, we can go up to 0, with a size of range of 0, which means we only selected one model. So now we have these 2 strategies, and it may be difficult to choose among them. One lucky result we had in this synthetic data is that the method with the lowest range on the left seems also to be the one with the lowest error on the right. So we don't know if this can generalize to other experiments. We need to do more. But that's an encouraging result because it means that we can compute both and basically trust the one with the lowest predicted range. In conclusion, this is a metric that we think can help selecting bias correction methods. We haven't seen it published before, so we think it's new, but obviously, just like Max in the first talk, if you know it, please raise your hand and tell us. It still has some flaws because you need to basically run all the methods you have at hand, and it will select a subset. It's not ideal. It's way more costly in terms of computation. Plus, the metric A2A for now is ordinal. It can tell you if one method is better than the other, but there is no absolute value, just like the SMD, that you can use for a threshold. But it also offers promising perspective. We believe that it can be extended to other methods than propensity score matching, so maybe the meta-learners we've seen before. And it can already be used in real cases for people who would like to use it. The most important part for us is that the people working on the social security data in France are interested to know about this method, so we are presenting it next month. We are also talking with APHP, which is a big hospital consortium in France. And so that may lead to something that will be actually used in real life, which would be the best outcome. For now, it's available as a research package on a GitHub account. It will probably never make it to a real package. The point is that there are already packages to do propensity score matching and bias correction, such as causal ML, econ ML. For us, it's more the R package matchit that seems to be very used in our cases. If we gain traction on that, the goal will be to have it integrated in existing package, more than having one more package for that. A point we wanted to raise about that is that this whole research, this whole project was done as a hobby. It's not part of my job. So we are looking for people who would like to participate in that kind of project, meaning instead of, I'm trying to steal open source contributors, but instead of working only on open source software, maybe you want to work on a full research project. There are a lot of advantage. For example, it only takes 1 to 2 years. If you compare to the 10 years needed to have your pull request merge in scikit-learn, it's nothing. And we have a very low burnout rate, much lower. We are looking for researchers that can give ideas and supervise projects, but also participants that have some time and want to work on it. And the goal to have everybody probably in a meetup is to create work dynamics, because people isolated tend to maybe get be less motivated and give up at some point. Help managing conflict, and most importantly, if you want to present your paper in a conference, get sponsorship, because it's expensive, and if you're on your own money, it can be a real burden. I've put a QR code here. You can scan it. It's a Google form if you want to participate. That will ask you if you're interested, if you want to participate as a researcher or as a contributor. And a lot of free field if you want to tell me your opinion. That's very valuable. That's all for me today. So I will now take your question. And thanks for your attention.
If there's any question, I don't see.
Thank you very much for your talk. You seem to be in the business, at least in the first part, of matching distributions and matching patients from the two different groups. I was wondering if at some point you thought about using optimal transport, and if so, why did it not make it up to this point? Thank you.
So Leo probably knows the answer better than me. I don't know if there is a method based on optimal transport.
But you mentioned it in your paper, no?
Hmm?
You do mention optimal transport in your paper.
Yes, I mentioned it. I mentioned it once. Yes. So, but I don't know if it's widely used. One thing I can tell you is that usually when you are dealing with the health authorities, they do not like brand new method, or they do not like creativity. They are mostly reassured when you use the plain old method from the 80s. So that's what we tend to take these methods rather than new ones. I must also mention that you have most recent work that propose, it was already said before, but that propose ways to validate the model, for example, by looking at the stability of the prediction. So you have ways to do it other than what we show. It's a more complex story.
If I can give a bit of a reply to this. Optimal transport. Sorry, my voice is dead. Optimal transport is about moving people horizontally. So it's about, changing people to match the distribution. This kind of topic is about reweighting people. So it's moving vertically in the distribution space, whereas optimal transport is moving horizontally. I'm sure there are some causal inference work that do optimal transport, but there is a fundamental difference in the two problems.
Thank you. Thank you very much for your talk. My question is, if you compute propensity score, is there some other constraints for example, how can you compute this on this data set? So my question is about filtering the ways you compute propensity score before you do your A2A method.
I'm sorry, I didn't get the end of the question.
Okay, so is it possible to first filter out some methods of computing propensity score because they are not applicable to your data set?
So not applicable. You can filter out based on some criteria. For example, propensity score usually must be in the range of between 5% and 95%. Some people tend to clip the values that are outside of this range. But I would say that if your method, for example, I've seen that with some neural network or random forest sometime. They are very confident in their estimation of the propensity, so they give you values between 0s and 1. So that's one way to do it. And also, if the distribution of propensity you obtain do not overlap at all, then there is no point in trying to correct them. So that's where you can do it. Otherwise, I would say the usual machine learning metrics, if you see that that your loss is not going down, it's not converging, stuff like that, that can be a signal.
Okay, thank you.
We have time for one more. Or we can go to lunch. So thanks again, Alexandre.
Thank you.